Okay, can you see the desktop okay? Hi, Karen. Very good. Welcome. Okay, tonight, first, are there any questions? Hi, Daniel. Sure, Karen. You have a question? Oh, I'm sorry. I thought you said you had a question. You said yes, you see the desktop. I get it. Hi, Kang. Hi, Fang. Kang, did you get my email back to your question? Yeah, I wanted to tell the whole class how I grade the project, so it would be too daunting on any one student. So let me get the project teams out. And I need to get checking done. On the project teams, when I formed the project teams, I'll explain to all of you guys. I did it based on test scores. So what I did was I just split up the people, right? I just went down like this. Here's the test scores of everybody, and I just picked and put people on each team so that I could get a good group of people on each team. And then the last ones, you can't tell because it's alphabetical which is which, but the last ones, maybe there were 6 or 7 students that didn't participate as much, and that's why I made the teams bigger. So 7 and 8. And I would expect that the teams with 8 would drop to 7 maybe, and the teams with 7 would drop to 6. So that I expect to happen. If you drop below 6, what I typically do anyway is I look at what each person produces. That's why I asked you guys to divvy up those deliverables so that I could then grade the deliverable. Like, let's say, I'll just give an example. So this may not happen at all. But let's take team 2. Maybe 2 people drop out. That leaves 5 people. And maybe the 2 people that dropped out, one was user view, and the other was processor stuff. And these guys did the other deliverables. I would grade them based on their deliverables, and I would skip the fact that those other 2 deliverables weren't included. So that way, it's fair for everybody. Did I answer your question, Kang, now? Okay. Yeah, don't be too concerned about that. I do want to make sure that you guys get to each of your team members, though. Some may not participate. They may even sign up for something and not deliver it. Well, they would get a 0. You guys would not. Those people that produced, when I get closer towards when it's due, I'll tell you how I want the first page to be. Basically, I want to know all the people and what they delivered on the first page. Okay? That should quell some of the fears that you might have about being in a team project. Okay. Are there any other questions about the team project? That was one that came in from email. Collaborate with who, Karen? Well, sure. It's your team. Your team can collaborate any way they like. Yeah, sure. Like if you needed some help on a particular aspect of maybe you're doing processor management and some other student has got some knowledge on that, sure. I mean, the whole purpose of this project is to learn. Okay, very good. Yeah. Let me say on the virtual storage concepts. First, I want to make sure we understand how it works. Okay. So I put this thing called completed. If it's not out there, I'm going to put it out there. But what happens is this. I'm going to explain how the program addresses get on the file, in the file. So let's do that first. I don't know where to put this. Let me do it this way. Okay, to get, this is your exe on disk that you're going to load, okay, from the loader. So, the virtual addresses in this example, I'm just giving you an example here, are 32 bits. Let's say you're doing a 32-bit address. You would have segment, 10-bit segment. You would have, for each segment, you could have 2 to the 10 pages. And a displacement within each page is 2 to the 12, which is 4K. So if you added up these digits, these bits, that's 10, 10, and 12, that's 32 bits. So when we break up a particular virtual address, you'll know the number of bits in each of the items. The segment 10, so 2 to the 10 would be 1024. So this a program can have 1,024 segments in it. Each segment could have 1,024 pages, and each page could have 4K bytes. And this virtual capacity in this system is 4 gigabytes, 2 to the 32. Okay? So I'm trying to explain it again. 2 to the 10 is 1024 1K. 2 to the 12 is 4K. So a program may have 124 segments. Each segment may have 124 pages. Each page has 4096 bytes. Okay, in the scheme I drew, we don't have that much in real storage. So we have in real storage 16 frames, and a frame has to be the same size as a page, 4K. All right, and we have 16 of them. So 16 times 4K is 64K. So I could have a 4 gigabyte virtual storage program running inside 64K of virtual scheme. Now that's kind of silly, but you could. So program A, in this example here, program A has 3 segments. Segment 0, segment 1, segment 2. Segment 0's size is 10K. Okay, that segment is 10K. Segment 1's size is 6K. Segment 2 size is 15K. So when the compiler sees this, what it does, it says, oh, I've got a segment, and it starts filling out page 1, which is page 0, first page 0, up until 4K bytes. As soon as 4K bytes is done, it stops that page and starts the next page. So it starts those bytes at 0 within page 1. So from 0 to 4095, 0 to 495. When it got to, now we've done 8K, right? There's 4K, there's 4K. It's got 2K left of the segment to put in. So it creates another page, page 2, starts at 0, and only goes to 2048 because it's only 2K. The remainder 2048 of that page is fragmentation, internal fragmentation, because the page isn't full. These pages, page 0 and page 1, are full. I want to stop a second. Is that clear to you guys? Any questions? Okay, that takes care of that segment. Then when the compiler sees segment 1, the next segment, it's 6K. So it just starts going down the same thing. It starts again at P0, and in the displacement, it starts at 0 and goes all the way to 4096, 0 to 495, and then starts page 2, which is, referenced by P1, and it's only 1K in size because it's 6K. It should be 2. I subtracted one. It's 6K. So I got the first 4, and then the next is 2K, and we have 2K in internal fragmentation again. Okay? So segment 1 has 2 pages, of which the last page has internal fragmentation. And finally, it's going to do the next segment, which is 15K. So it goes back to P0, and then it starts in displacement 0 all the way to 4096. Then P1 starts at 0 again, goes to 4096. P2 starts at 0 and goes to 4096. I should say 4K. I must put that K out. Okay. It's over a little bit. And then starts P0, starts at 0 for the displacement again, and goes to 3K. And then 1K is internal fragmentation. So that's what's in these pages right here, is a program that is 15K in length when it was compiled. Now it's a little bit longer in length because of its page size. Okay? It's a little bit longer in length. Any questions on that? Now that the addresses are compiled, and they would look like this, so let me just show you one. Okay, I'm going to use binary because it'd be easier to do that. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's segment 1. 0, if it were 0, it would be segment 0. 1 would be segment 1. Now let's get the page in. So I need 1, 2, 3, 4, 5, 6, 7, 8, 9. 1 would be page 1. So we're looking right at this page right here. Now it's only got 2K. So the displacement let's do a displacement, which is 12 bits. So 1, 2, 3, 4, 5, 6. 1, 1, 1, 1, 1, 1, 6 times. That's the address of the displacement. And that would be an example of a page, of a byte generated as a virtual address. The first 10 bits represents the segment number. The next 10 bits represents the page within that segment. And the last 12 bits represents the displacement from within that page. Is that clear, first of all? Albert, Daniel, Dang? Anyone? Okay. Okay. I just want to hear a confirmation that it's clear. So here's what the loader does. The loader is going to load the program, and it puts it in the paging device on disk. And every one of our programs here in Windows, everything here that's a user program, is on a paging device. And that's how it maintains the program, and any data is in the paging device. And we'll see that in Chapter 9. Now, while it's loading this, it says, oh, I have 3 segments. So it creates this here. I'm kind of showing you. This here is in memory, right here, these tables. They're being built by the loader. So it places it on the paging device, and then it fills in these tables. So let's look at that. Here it is on the paging device. So segment 0 has 3 pages, and its address on the paging device is X, and that's what this represents. So we know where it is, where that segment is on disk. Okay. Y has 2 pages, and we know that that's a pointer to where it is on the page, on the paging device. And then Z. Okay. And we build the tables. So segment 0 has 3 pages. So when we build the page map table. And when we build the table, we have a pointer from the segment map table for that segment. So this segment has 3 pages, and it has a pointer from here to the page. Okay? I'm just illustrating how the loader is loading all of this. Then we have a pointer from the segment 1 to the 2 pages that it has, and then we have a pointer for segment 2 to the 4 pages that segment 2 has. Okay, then it turns, now the loader would then turn it over to memory management. And memory management, the virtual storage management, would then decide, well, where am I going to put it in memory? What are my free page frames? And then it decided, that it's going to load segment 1, segment 0, page 0 into 5, into that address. And it puts that pointer or that address right there. Okay? It also loaded, oh, and it flipped this valid bit. This is called the page valid bit. If it's 1, it's valid, meaning that's a valid page. 0 meaning it's not valid. It's not in memory. Okay? And it loads this page. And it gave it 9. So this would have the address of 9. And it flipped this bit to 1. Okay? Now, whenever it flips one of these bits on a page to 1, it flips the segment as being partially loaded. This is a valid bit of 1 here. This is a valid bit because there's at least 1 page loaded. This is 0 because there's no pages loaded for this segment. Okay, now typically this stuff that's in blue is not in virtual storage. This is real memory because it needs to be accessed quickly. You're not gonna have this in a virtual storage scheme. So this is in real storage. We talked about real storage on Tuesday. This is your virtual storage area, and typically it's for end user programs. It could be also operating system programs, but typically it's user programs. Okay, I want to stop. Are there any questions about what's happening here? Is that clear? All right then, if that's the case, then let's do this. It's going to be kind of hard to show this. Let me do it this way. Yeah, let's do it this way. Here's my virtual address. So I have a segment number, which would be this number, 0, 1, 2. It would be one of those numbers. I have a page number within that segment, 0, 1, 2, 0, 1, 0, 1, 2, 3. Those would be those addresses I showed you before. And then I have a displacement or offset within the page. So the dynamic address translation function is the following. When I start up program A, I find this pointer for program A segment map table. I place that in a special register in the CPU, and I load up the first address from the program. It's a virtual address. It might be 0, 0, 0, 0, 1 or something. It might be the first byte or something. But segment 0, page 0 would be the first one. So from a copy program on disk into paging device, OS builds the SMT and PMT for each of the segment map tables. The location of the segment on disk is stored in the SMT for each segment. That's this, the address on disk. Okay. All valid bits are 0 until a page is placed in the page frame. Assume the first address, is 0010. Okay. Then the OS loads S0, P0 into a free frame. In our example, frame 5. Okay, we loaded in frame 5. Okay, assume the next address is 00100. Then dynamic address translation would see a 1 valid bit here. So the dynamic translator looks here first. Is it in memory? Is any part of that segment in memory? Yes. Continue. Pull up this address of this. Okay. It sees a 1 right here. All right, it would see a 1 valid bit because, in this case it wouldn't. Dynamic would see a 1 valid bit in SMT, but 0 valid bit for page 1, right here, this guy. So it would be a page fault, and that page would then have to be loaded into memory. Okay, let's make another assumption. Assume the next, let's say that page was taken care of. Assume the next address is 1020. All right, so segment 1, and part of it's in. We chase the chain, and we go to 0, and it is in memory. And then it's a displacement of 9. It would, whatever this address, it would add 20 to that, and it would fetch that data. Okay? Assume the next address is 20100. Well, 2, it would get a segment fault right away because it's not in memory. I mean, it's not in any of the pages, so it's not in the page frames. I want to stop a second. Are there any questions about these examples? Is it clear as to how the loader loads it, how the virtual addresses are coded, and the address translation occurs from these tables? Hi, Bayo. Well, they're here in the notes. In the notes, I put the same information so that you could look at that and see and look at it later when you have more time to think about it. All right. Okay, Chapter 9 has to do with virtual memory management. How do you manage this environment? So we're going to go through these items, okay, and try to illustrate some of them. Well, the benefits of a virtual storage system is really easy. And what it is, it goes back to, well, we'll see it in a second. First, if you don't have enough physical memory, your program could have a lot of virtual memory. I just went through that with you with this example. We have this scheme, right? We have this scheme here where we have a virtual address that can go 4 gigabytes, but real memory I only have 64K. So of virtual memory. And I could run those programs. It would run very well, but I could run them in a much smaller memory location. And that's where this concept really came from, because memory was really expensive back in the 1970s and 60s when computers were first being created. Now, I mean, it's like memory's pretty cheap. So that was one. It separates logical from physical. Only part of the program needs to be in memory, whereas remember we talked about real memory techniques. They had to be contiguous. The whole program had to be in memory. That's not true of this environment. Logical can be much larger than physical. It allows the address space to be shared by other processes and allows for more efficient process creation. There's two different concepts here, demand paging and demand segmentation. I'm using combined segmentation paging in my example because most systems use 2 levels. Some even use 3 levels. We saw that in Chapter 8. This is another look at what it looks like. The virtual address space concept. And you could share libraries. So you could have pages that are shared. And on Tuesday, we talked about sharing segments and sharing pages, and it was easier to share segments, pure segmentation, than sharing pages. All right. There's 2 kinds of concepts here: demand paging and anticipatory paging. He talks about it in a little bit. Demand paging means you load a program, you load a page when it's needed. For example, if I get a page fault, that page isn't in memory. That's how I got a page fault. That's called demand paging. When I need a page, the programs reference the page, bring it into memory. That's demand paging. Less I/O needed, less memory, faster response if you have more users. That's what would happen. A page is needed, reference to it. Invalid bit reference, we talked about that. You abort that. It's not in memory, bring it into memory. The swapper never swaps a page in memory unless a page will be needed. That's called the lazy swapper. Swapper that deals with pages is a pager. Okay. It's kind of funny. When you're transferring segments, right? Remember segments in your program? That's why I like segmentation, because you could transfer a whole segment of those pages into memory. So you could swap them in, and you could swap them out if they happen to be contiguous in this case. So it's much faster on your disk I/O functionality if you store your stuff on pages in contiguous order in a segment. And that's why I did this. I stored my 3 0 to 3. My 3 pages, yeah. My 3 pages at this location in disk. Okay. I didn't happen to do it here in real memory here, the page frames. I didn't store them contiguous, but I did on the disk. So I could load them like I could load with this one as an example. We have 4 pages, none of which are in memory. And if I have A, B, C, D free, I could load them right in there directly. And that would be a quick I/O. And that's what he's talking about here. I talked about the valid and invalid bits. I talked about what happens when pages aren't in main memory. You get a page fault. So it has to look at another table to decide what to do. Okay, it's not in memory. You get an empty frame. You have to find an empty frame. Swap the page into that frame. You reset the tables. You set the valid bits. So after I put a new page in, right, I set the valid bit. I set up the table with the address. I set the valid bit to 1. I'd probably reset this guy to 1, but it's already 1. And then I'd restart that instruction because it failed. Now it will succeed and go through the address and find the correct address. And that's why I said restart the execution that caused the page fault. They're just showing you continue that. And these are just the same steps in handling a page fault. Okay. And then there's some calculation. I don't really put this on the test, so we can skip over it. You can look over it. It's interesting stuff. When you have virtual memory, you can get the copy on write concept, and you can get memory map files, which I think we'll talk about either later in this chapter or in file management. So copy on write. So I'm sharing a process, and I'm sharing a page. Okay. If I make a change to that page, the other process may not need that change. This page is being written to. I need to copy it to another page and point that process's page map table to the new page that I created and leave the old share pointer set to the read-only one. And that's what copy on write is really doing. It's pretty efficient. So think about it. Copy on write is more efficient. Only modified pages are copied. It's getting closer to our exciting algorithms. We're going to get there. This is just an example. Now we're there. What happens if there's no free frame? It's called page replacement. Find some page in memory, but not really in use, and swap it out. Okay, this is really critical, so I'm going to come back to this. Suppose this page that's being used by this program is going to be replaced because there are no other free pages available. All these 16 pages are used, and another process needs a page. So you look at and you figure out what page I can replace. That's the page replacement algorithms we're going to talk about. And they're fun, so we're going to go through those. But what you have to do is, if this page has been modified, it must be rewritten back to the paging device so that when you reload this page, it has the correct data in it. And the paging device always has the correct data values in it. It has to. Okay? So there's going to be some differences here. I mean, as this is getting written, it's not going to keep writing this every time. It's going to write the page back when it needs to write the page back. And the only times I could think of that is if we're going to replace this with another page, right, from another process, and we modified that page. If we didn't modify the page, who cares? It wasn't modified. But if that page was modified, we have to make sure that we copy it back to the paging over here so we don't lose its contents. Just in case we want to reload that page somewhere else, it's got the correct data. Does that make sense, everybody? Albert, are you following? Bang, you okay? Okay, very good. So, page replacement is the key concept. You have to understand there's a dirty bit to reduce the overhead of page transfers. Only modified pages are written to disk. So, let's go back here. There's these bits in here. I didn't identify these bits in here, but one of the bits could be during a store instruction. Okay? During a store instruction, this bit is split to being modified. Okay? Once again, that's how it would know that this page was changed. So basically, once I have a store instruction, and usually store instructions are separated. If you ever look at a processor, it's basically typical separation between reading instructions and storing instructions. So it's pretty easy to determine. And when I talk about the translation look-aside buffer, I talked about it on Tuesday. I want to bring it back. It would also be in the translation look-aside buffer that we did a store on that guy. All right, let's go back to this. So that's the dirty bit, or modified bit, either one. Okay. All this is describing is we need to put a page in memory and replace it. Okay, we need to replace a page. We don't have any free ones. So there's these basic page replacement algorithms. First one is find a free frame. If there is a free frame, use it. If there's no free frame, use a page replacement algorithm to select a victim frame. Oh, you love that terminology. Sure, Ken, I understand. So now we're talking about, well, how do we pick the victim? There are page replacement algorithms. Of course, different kinds. We want the lowest page fault rate. Evaluate algorithm by running it on a particular string of memory references that compute the number of page faults on that string. And you can count the number of page faults. When a process does a page fault, you can count that because you've got to bring that page into memory. And there's an example of the number of frames and the faults. Okay, number of faults drop, right? This is the number of faults. 16 drops down to 8 to 6. If it has 5 frames, right, it gets 4 page faults. So as you increase the number, you get less faults. Number available for that process. So here's our first algorithm. It's called FIFO, first in, first out. So assume we have 3 frames and 3 pages can be in memory at a time per process. And these are the reference strings of a process. 1, 2, 3. So it's got 5 pages. Okay, it's got 5 pages in this particular process. And we only have 3 frames. So we would load 1, 2, and 3. Then we would load 4 in 1. And then, see the next one, first in, first out. Then the next one would be this one. And the next one would be 2. Okay. Then 5. Then 1 is already there. See, 1 is here. So that's not a fault. 1 is already in. That's not a fault. 2 is already in. So that's not a fault. 3 is not in. And that's why 3 is here, replacing 1. And 4 is here. So that's, oh no, excuse me, 4 is gone. 4 is in here, so we replace it. And finally, 5 is there. So if you counted those up, you would have 9 page faults. Yes, that is correct, Ken. If the page is not loaded that's required, if a page here, a page in the program. Remember these pages here in the program. If that's not loaded into the virtual page frame, it's not in main memory, that's a page fault every time. And that's what it's illustrating here, is this is what pages are going to get referenced, and these are the frames for the pages. And if you added those up, I did for you, it would be 9 faults. 1, 2, 3, 4, 5, 6, 7, 8, no, 8, 9. These 2 were in here. When we did 1, 2, they were in there. So we didn't have to fault that. They were in here. 1 and 2 were here. So that got us the 9. Now, if we increase 4 pages, so now we have 4 pages, but we get 10 faults on the same set. And this concept is called Bilaty's anomaly, where more frames is equivalent to more page faults. It's kind of an oddity. That's why it's called an anomaly. And it occurs on this algorithm. And yes, you have to understand this algorithm, first in, first out. And I'll illustrate to you guys before the test. I'll illustrate what this problem is going to look like on the test. And there's the replacement strategy with 4. And this illustrates that. I'm not going to spend a lot of time on it. Okay, this is the optimal algorithm. And I call it POO, P-O-O, Principle of Optimality. That's what a lot of authors call it. He calls it the optimal algorithm. I call it POO, P-O-O, Principle of Optimality. Okay? So if you're going to use POO, it says replace the page that will not be used for the longest period of time. Doesn't that make sense, guys? I have all these pages. If I have to pick one to replace, I'm going to pick the one that's not going to be used for the longest time in the future. Well, this sounds like Back to the Future concept. And believe me, it is. How do you know this? How do you know which is going to be the one that's most used in the future unless you started to run the thing? That's the problem. That's why I call it a principle. It's not an algorithm. It's a principle. It's a principle. You want to replace the page that will not be used for the longest period of time. You can't implement this as is. Okay? It's not possible. Now, I can say this. Processors today are doing these what-if kinds of things to try and answer this question. And I get really worried when the CPU, like Intel people, try to implement this in hardware. There's so many issues around that. So anyway, this is optimal page replacement. It is the best, but it doesn't exist. So we're going to get close here. The next one's called least recently used. So what you're going to do is every page entry has a counter. Every time a page is referenced through this entry, copy the clock into the counter. When a page needs to be changed, look at the counters to determine which are to change. In other words, the least recently used. So, here's the concept. Every time a page is touched, you put a timestamp on it. Timestamp, timestamp, timestamp. And then you search the stamps looking for the I guess it would be the oldest stamped page. You know, one farthest in the back. Hasn't been referenced for a while. Does that make sense? Guys? Wait, guys. Okay, I see people are typing. Are you asking your question? I don't see a new question. Okay. The issue with this is, imagine the amount of hardware needed to implement that. It's just an awful lot of hardware to do that. So this one is a good concept, but very difficult to implement. Mainframes have that. You know, really expensive processors. They use this concept. All right. Okay, you have this concept. Instead of maybe it's up one. Let me see. Is it here? I don't. Least recently used algorithm. Yeah, that uses a timestamp. Now there are approximations. Remember I said it's difficult to implement this? There are different algorithms that try to approximate this. And one is not used recently, NUR, and the other is second chance clock replacement algorithms. All right? And I think there's a diagram that explains this one. Yeah. The way second chance works is this. Each page is referenced, whether that page has been referenced, it has a bit, 0 or 1. So when it's 0, that page has not been referenced. When it's 1, it's been referenced. In other words, it's been used. So the idea is, in your page map table, you would have a reference bit and a modify bit. Okay? I talked about the modify bit, the dirty bit. We would also have a reference bit. As soon as this page gets hit by the CPU, you would set this to 1. Okay? And what this reference does is it goes around looking for zeros, not reference. Okay? So it looks at this and says, oh, this is 0, 0, that hasn't been referenced. This is like the next victim, right? In other words, our pointer's here, and then we move it here. Well, this one's been referenced, so we won't use this. This one has not been referenced, right here. It has not been referenced. So we set it, we use it. We'll use this guy. Okay? And if we don't have any to pick, we come up and around. I know this is a little confusing. I'll try to clarify it in an example. So let me see. No questions yet. It's called second chance or clock page replacement algorithm. Okay, the last algorithms are counting algorithms. Least frequently used, smallest count, most frequently used. The based on the argument, the page with the smallest count was probably just brought in and is yet to be used. This one says, this page has been used an awful lot, replace it. That's what counting means. I'm going to have a counter on each page. So once again, every time I hit that page, it's been referenced, I up the count. I up the count. I up the count. And then when I need a page, I look at the page map tables, counts, and if I'm using the least frequently used, that would be closer to 0, I would pick that page. Most frequently used, it would be maybe 1,000 or 2,000 or 10,000. I would replace that page. That's the argument. Okay. We're getting to a concept that's another concept. And it has to do with a minimum number of pages for processes. So, for example, you might have each process needs a minimum number of pages. In the mainframe uses this. And they have two major allocation schemes: fixed allocation, priority. Either of those. No, there were no questions. There was no type. People look like they're typing, but there's no question. Okay. So fixed allocation. You don't need to know the algorithms, guys. These mathematical things. Priority is pretty simple. Global versus local. Okay, let's look at that. This is all my systems frames. So that would be global. These pages that are allocated to my process are local. So right now I have page frame 5 and page frame 9 allocated to program A. And maybe those are the two I would use for my other pages. That's local. That's the definition. Each process selects only within its own set of allocated frames. That might be on the test. Definitely this is on the test. I remember there was a question about this. Okay, so if a process does not have enough pages, the page fault rate is very high. This leads to low CPU utilization. The operating system thinks it needs to increase the degree of multi-programming, and another process added to the system. This makes this worse. So thrashing is a process that's busy swapping pages in and out. Thrashing is this, that in your system you are taking pages out, writing them back on the disk, bringing other pages in, and then paging it out, bringing other pages in, and you always see this thrashing when memory is very low. The real memory is very low. So right now I've got quite a bit available. I've got 1,702 pages of physical memory available, and you can see that the kernel memory, some of it is paged, and non-paged, those are the tables in the operating system. The non-paged, the tables in the operating system, the handlers, operating system handlers are that. So there's a bunch of memory for that. Let's look at Resource Manager, because what's interesting about Resource Manager is when you go to memory, it actually shows you the fault rate. yeah, fault rate, here it is. This is the hard fault rate, and I don't have any. It's because my memory doesn't need it, so I have no faults right now in my all these processes. They're not faulting. So that's a good thing. They're all in main memory. But when you get main memory being overused, right, you'll start to see a lot of faults. Okay. And this thrashing. And what I typically tell people is if you start up a program and you look down and you see your disk light flashing like crazy and nothing else is really, going on, you're probably thrashing. Okay. Oh, this is one of my favorite diagrams. Each one of these is a page, and what you're seeing across time, right to left to right, is the CPU hitting those pages with instructions. And this is typical of programs, the way they'd operate. You would start out, your program does some setup kind of work, and then it goes into maybe read some data. And this definitely looks like it's a loop here, in a loop. And this looks like it's in a loop here that calls this guy. Then something happens here in the program. It ends with that loop, does a couple of things, and now he's really covering these 3 pages like crazy. Then goes down and does a little bit here, and then spends a lot of time here, a little bit of time up here, and flashes through here, a lot of time here. And then all of a sudden something completely changes in the program and goes into a different set of routines and is spending its time here in these pages that haven't been hit at all, and then finally ends up. And this is very typical of a memory reference pattern. So now we go to the next model, working set. Working set is you define a certain set for your process, for every program, and that's your working set. Okay, if your size of delta is the number of your working set, the fixed number of pages in your working set. If your delta is too small, you're going to encompass entire locality. I forgot that he was talking about locality. Locality means this. This is locality. Is where do you spend most of your CPU time, in what area of your program? That's locality. And that's what I was describing here. I forgot that he mentioned that word there. But yeah, this talks about locality. You don't see every page being hit here. You only see certain pages being hit for a period of time. And that's typical of programs, right? Especially anybody writing loops. Okay, so if your delta is too large, you'll have several localities. You have too many pages. That's the idea of working set. It works on this concept of programs usually run in a number of page frames very effectively, and that's the locality at that time. Now the time may change over time. So we have page reference table, okay, and this is the delta. Then it becomes this delta. And you just keep track of the working set. The way I am going to use it for you guys is the number of pages rather than over a period of time. It'll just be the number of pages that we're dealing with. And then you can get the concept of looking at page fault rate. What's the page fault rate? So you established a quote, an acceptable page fault rate, whatever that is. If the actual rate is too low, the process loses frames. If the actual rate is too high, the process gains frames. In other words, you want to find the right mix where the process doesn't do a lot of page faults. It stays within the page faults that you've set. And it's okay to have page faults. So that you can change your working set, how many page frames you're going to allocate over a period of time. You can change that based on your page fault rates. Okay? So if you're faulting a lot, you may give it a few more pages. And that works pretty well. Oh, he does talk about memory map files here. I want to stop a second here and kind of summarize for you. Okay, so this is the kind of thing I want you to know. So first, I want you to really understand dynamic address translation. By that, I mean I want you to really understand how a virtual address using these tables gets converted to a real address in memory. That's dynamic address translation. That's going to be worth 8 points on the next test. It's that important. And I'll illustrate how that problem's going to look. Then you need to understand the page replacement algorithms. Who? Principle of optimality. Replace the page which will not be needed until the furthest time in the future. And you know you can't implement that. FIFO. First in, first out. Date time stamp with each page when paged in. And you replace the oldest page. Okay, so basically the first page that you brought into main memory would be the first page you replace when you need to replace it. That's the oldest page that was brought in. So basically the timestamp on this one isn't too bad, except it falls into that anomaly issue. I lost my page. Yeah, I closed it there. On the page map table, you would have a date timestamp when that page was brought into memory. And it really makes it easier because you don't have to worry too much about setting counters and all that kind of stuff that we're talking about. Okay, another one is least recently used. You have a timestamp on each reference, not when it's paged in, but every time you reference the page, you get a timestamp, then would replace the oldest date. So that's least recently used. Clock replacement. On the second chance, and it tries to emulate least recently used. Tries to emulate this concept if you can't implement it through hardware. Okay, next concept is counts. You have frequency, so you have a counter. You replace the page that has the oldest or the largest counter, or you replace the page that has the least counter. The next is working set. You give the process a number of pages and you watch its page fall. And if it's faulting a lot, give it some more pages. If it's not faulting a lot, take some pages away. But pages will be local. In other words, all of the pages I replace within that process. That's what this means. Local. I'm not giving this process the global pages. And you remember the difference between global and local pages, right? Global is all the page frames. Local is those pages owned by the process. Okay. Not used recently. He doesn't talk about this, but other books have. He kind of referenced it, but he didn't call it not used recently. So I want you to know this one. So I'm going to take you through this algorithm here. You have 2 bits on each frame, right? And you can implement them. You can implement them by having these bits in here for the page. And I've already talked about the 2, so let's. I've already kind of talked about the 2 of them. They're the reference or access bit. This is the reference or access bit, and the modified bit, that page has been modified. So what you do is you just have, for every page, you would have these 2 bits. Every time it got hit, it would be set to 1. Every time it got modified, it would be set to 1. Periodically, the system has to reset all of the access bits to 0 to restart it. Very much like the clock, which I'll illustrate for you, the clock policy one I'll illustrate. And this would be the order of replacement. So the order is 1 to 4, and this is the access bit, this is the modified bit. So the first one to replace would be 0, 0. The second one would be 0, 1. The third one would be 1, 0. And the fourth one would be 1, 1. Now, a question you might have is, how could this happen? How could it be modified and not accessed? Well, what happened was it was accessed and it was modified, but this periodical reset all of the pages to 0, and since that period of reset, these pages were hit. They were referenced. So we know it was referenced, and it hasn't been referenced since the periodic reset. Therefore, it would be number 2 in the order of victimizing it, replacing that page. So this is a cool algorithm. And it's fairly easy to implement. Some of these others are a little tougher. The clock policy one is kind of a modification of this. Okay? It's not quite this one. I believe I have a homework question for you guys that talks about the clock policy one. So when you do that, I think it'll become clearer. You might be right. Oh, this is my other class. I only have that class. Let me get you guys. We need to go over the CC Confer question of the day before it gets too late. I'm just looking at Chapter 8. My guess it would be in Chapter 9's questions. Yeah. Second chance is the clock replacement guy. Yeah. That's close. Let's go to the question today. I'll talk about it here before we see the question. When dynamic address translation was first invoked, right, and we're talking now in, Intel's earlier versions of it, the 286, the 386, the Pentiums, those guys, in their documentation, they said that virtual addresses go through their address translation scheme and become effective addresses. The word was effective, meaning physical memory addresses. Okay? And that word was used back in the 1980s, 90s. I don't see that word being used today, but I put it on the quiz. So you'd have to see this question and review the session in order to get the answer. So Art said that in today's terminology, a physical address, actually it should say yesterday's terminology. Not so much today as it was yesteryear. Let's try that. And that's correct. So you guys got it, right? Albert, Beo, Daniel, gang, you got it. Okay, just checking. It's always nice to see stuff. Okay, let's go on to another topic. The concept is pretty much like this. I've got these pages in memory. Why can't I do the same with, not just with programs, right? But when I deal with opening a file and reading file contents, I mean, I have to open the program as a file, and the program, you know, does these things. That's why they're programs. They do this. Files don't create they don't create page map tables, etc. But files could. I could have a memory mapped file and use the scheme to locate that file. I could use something very similar, scheme. And that's this concept of memory map. So it's initially read using demand paging. A page-sized portion of the file is read from the file system into a physical page. Subsequent reads and writes to and from the file are treated as ordinary memory accesses. It simplifies file access by treating the I/O through memory rather than read-write system calls. So you're actually, if you want to look at it another way, probably a more easier way to look at it is, this is a buffer. Your memory is a buffer, huge buffer, for any files that you're reading and writing. like this file right here. This file that I'm reading and showing you in format from PowerPoint, this PowerPoint program opened this file. This file is in virtual storage, being treated just like a file, like memory. And there's the illustration. And the nice thing about this is you could share these files, through different processes. You can share the disk file. Okay, there's these blocks of files that read into memory here. So that's pretty cool. You would need a pointer, right, when you open the file. When we talk about file management, we'll talk more about what's in the file map table, the FMT. And this is an example, I guess, in Windows, how it shares memory. Okay, now, normally, user memory is in virtual storage. We talked about parts of kernel memory. The kernel memory, parts of it's paged, and parts of it's not paged. And that's true if you think about what you don't want your tables, these tables. You don't want these tables in virtual storage. These tables are in real storage so that the CPU can access them rather rapidly when it needed to. Where the heck I was? Oh, right here. So you process it different. Often allocated from a free memory pool. Kernel requests memory for allocation of varying sizes. Some kernel memory needs to be contiguous because it's in real storage. It's not in a paged device. It's not being paged. It might be swapped out, but it's swapped out as a complete page. I can't remember if this is on the test. This concept I would like you to really look at if you're going to use Unix, you're going to do Unix or Linux or any of those operating systems. Take a look at the buddy system because this is where it's coming from. This concept. And it's this kind of idea. Is you have one block of contiguous pages. And then if you need some, you break it up into a block half the size. Right? And then if you need less, you break it up into half of that size. And if you need less or use less, you break it up in half of that size. And you stop at some level. What level you stop at. But eventually, when those are free, you would reallocate it back. Like when these two are free, you would get this block. When these two are free, you would get this block. When these two are free, you would get that block back. And that's the idea of buddy system allocator. And because it's the power of 2, it can be really easily programmed. The next one is slab allocator, and a lot of systems use this concept of slabs. It's one or more physically contiguous pages. That would be a slab. And a cache would consist of one or more slabs, cache of memory. A single cache for each unique kernel data structure. So each cache is filled with objects and instantiations of the data structure. When the cache is created, it's filled with objects marked as free. When the structures are stored, it's marked as used, so you know. If the slab is full of used objects, the next object is allocated from an empty slab. If no empty slabs, a new slab is allocated. Keeps using more memory. Benefits include no fragmentation, fast memory request, satisfaction. So it's a concept of slab allocator, where you have a huge block of memory and you just break them up into contiguous pages, and you create a slab. It just depends on how much system you need. For instance, remember we're getting back to this. Let's say I have, it doesn't show slabs here. I'd have to think about Windows and how it allocates memory, and I don't recall that. But we show all processes. And I've got, I'll do it by user. So system, I got all these system processes that are running, and I've got a couple of local processes, and the rest are I started, apparently, my user ID. And you can see the memory on all these system processes, what's being used. And like some of these are programs that are like Adobe. I mean, this has got to be it's started by the system, but it's a user program. So this is in virtual memory. So it doesn't really show you there. Now let's go back to performance. Resource monitor. Memory. Yeah, you can kind of see all the different processes that are running and what they're working set. So this uses the concept of working set right here, Windows. Okay. Well, at least we've seen it. That's the slab. Any questions on slab? I don't remember if I had any questions on the test on slabs. I might. Some other issues. I mean, this is outside, talking about paging and virtual storage. To reduce the number of page faults, you pre-page. You kind of figure out, well, if it's going to want one page, why not load all 3 pages of this segment? Right? If you've got it, load it. Same thing here. Load it. You can load the whole program if you have enough free pages out here. So that's the idea of preloading before it got hit, before it got needed, demand page. So this is actually called anticipatory paging. That would be another algorithm. Pre-paging, anticipatory paging. Same concept. The page size. You can some systems allow the page sizes to change anywhere from 2K to 16K size pages. And that affects your table size and locality, right? If your pages are larger, chances are you're going to have more inside that one page. Overhead, if the pages are larger, it's going to take longer to load that page to and from the paging system. So if these pages are huge, it's going to take longer to load back and forth. So you've got pros and cons for using different size pages. Also, you have the issue of fragmentation. If in our example here, right, I used 4K size pages, but suppose they were 16 size. Well, I would have fragmentation like crazy on this scheme. And that would be internal fragmentation within that process. Is all of this making sense, guys? I don't know. There's no questions. Finally, the translation look-aside buffer. Very important to understand. What is not shown in the CPU here is the TLB. The TLB, translation look-aside buffer, every time it loads a page, right, on a page fault, loads a page, it keeps track of that page in a translation look-aside associative memory buffer that has the address of that page. Okay, so I've got the process ID, I've got the page identifier, so it'd be segment 1, segment 0, page 0, I'd have those two, and then I would have the number 5. So it would be 005, so that when I get another instruction at 0010, I look at 00 and say, oh, that's at 5, that's at in address 5, and so I add that offset, and I'm off and running. You want the TLB to get as many hits as possible, because if you don't, you have to come out to memory and get that page, right? And then the page has got to get loaded from disk. If it's a page fault, it's got to get loaded from disk into memory. You update the TLB. You update the cache with that page, because now it's going to be fetched. So a lot of stuff is going to happen in the hardware. Okay. Anyway, this is just going through some of the issues of if you have different page sizes, how that affects your TLB reach. And I guess the last issue, well, how do you design your programs, right? If you, each row is stored in one page, right? If that were the case, you would have 16,000 page faults, apparently, for this program. Whereas if you designed your program this way, you would have 128 page faults. I'm not going to go through the programs, but it looks like you've got a two-dimensional data array, and this one goes what? It goes J less than 20, so it's going J over I. So it's going for each column, it's checking the row. So yeah, that would be inefficient. Whereas this one is for each row, it's checking the column, because normally data structures are stored row, column, row, row, and then all the columns. Row, all the columns. Row, all the columns. It's stored in that manner, and reading it this way is going to be really crazy. Whereas reading it row, column, you'll get all of the number of hits that they say. Does that make sense to you guys? Are you following what I'm saying? Have you guys written two-dimensional array programs? Yes. Okay. Sometimes when you're doing I/O, right, sometimes you may have to lock the memory because something's happening on that device at that time. Remember, we're doing memory mapping I/O rather than direct I/O from the disk. Okay, I'm not, yeah, reason why frames used for I/O must be in memory. Yeah, because you have buffers, and we talked about the buffers being pages. In this case, it looks like the buffer is just a couple of pages, not even the whole thing. And this is very typical of a lot of programs. They may look at it this way. I believe when we talk about file management, I'm going to illustrate buffers in the program. I'm not going to go through these because you guys are going to pick an operating system. Okay, we have about 20 minutes or so. There's a chart I would like to share with you. I don't think the chart is here. Let's see. No. No, it's not. Let me find it first. It's not there. It must be here. I don't see any samples. I don't see any samples. I was looking for the sample. Those are all the real tests. Replacement algorithms. Here they are. And yeah, good. Okay, I'll review this before the test. But this is the 5-point test problem that you're going to see. So let's look at it. Process X had been executed. The last access was in page frame 004. It has 2 pages in memory and has had a page fault. Okay, so here's X in page frame 02 and page frame 004. Using the information provided, answer the questions below. Note, these are all the page frames, and clock policy follows frame numbers. So what I mean by that is the clock policy is going to go like this. It's going to go like this. It's going to go like this. And I'll show you how clock policy really works. It's not hard. But this is the next one to check. You just got to have a point. Okay, here's the time it was loaded. That page was loaded into memory. Oh, by the way, all of these occur on the same day. So this would be like hour, minute. Okay, hour, minute. Enter time are all of these when they were loaded. This was the timestamp it was last used. And this is the use count, the number of times that page was used. Okay? So, the question is, what page frame, 1 through 6, would be replaced if we were using least frequently used replacement strategy. Okay, you guys, what would be used? What would be replaced? 5. Least recently used. No, frequently. Frequently means count. So 90 is correct, so it would replace, in fact, it's typed right. It would replace 5. Good job. Okay, somebody else. Least recently used. What page would get replaced? Anybody? Deo did one. How about one of the other guys? Daniel says frame 6. So, last used is least recently used, and that's right, that was the oldest. So, it uses military time, right? The hour, military time. Yeah, so 6 is right. All right. FIFO. Somebody else. Dang. 1. Yeah, 1 is the oldest frame. So you're right. It would replace 1. Very good. All right. Clock policy. Let me show you how it works, and then you tell me. If it sees a 1, it sets it to 0 and goes to the next one. Sees a 1, sets it to 0, wraps around, sees 1, sets it to 0, sees 1, sets it to 0, sees 1, sets it to 0, sees 1, sets it to 0. This is 0. That's the one that's going to get replaced. That's how it works. So, what one would it replace? What page frame? Anybody else? Albert, are you there? No? Good guess. Okay, I'll do it again. The way the algorithm works is the pointer says where to start next, and it just circles around. That's what clock means. If it sees a 1, it sets it to 0 and checks the next one. It's a 1, sets it to 0, wraps around, sees a 1, he's looking for a 0, sets it to 0, comes down, sets it to 0, comes down, sets it to 0, comes down, sets it to 0. This is 0. What would it replace? Right. It would replace 5. Good. Good. Okay. Now, what happens is this is a reference bit, guys. In other words, as it's going around, these, it sets it to 0, right? It sets it to 0, sets it to 0. This is being referenced maybe right away. So it gets back to 1. What this means is every time that page is referenced, it's set to 1. And that's how it gets set. That's why it skips anything that's 1 and goes to the next one. But it sets it to 0 as it leaves and checks the next one. So that if it comes around and this is still 0, that page hasn't been accessed since it's been all the way around. That's called second chance. Got it? Now your question should be, well, wait a minute, suppose it's gone around once and they're all 1s. Well, it'll go around again. And if it goes around again and they're all ones, it'll go around again. And what it needs to do after a certain period of time is just pick one, because it'll be in a loop forever. Yeah, you always start at the next pointer. It's the next one to look at. Okay. Working set. This is a little tougher. What page gets replaced? I'll give you a hint. What does working set mean? Replace the pages that are allocated to the process. What process is executed? What's the name of the process? X. Okay. How many pages does X have? Okay. What page was it executing in when it got the fault? Previous to the fault. It says the last access was in page frame what? Right. So would you replace 4 since that was the last access? Or would you replace 2? Well, the answer is 2 or 4, but more reasonable. It's 2 or 4, but 2 would be the one, because 4 was just last access, and it could be calling, right? This routine could be calling a subroutine that's in another segment, right, or another page. So we're going to come back to this routine after the call. You see that? So 2 is more the answer, but in this case, I would probably accept either. And this is what is going to be on the test, except the numbers will change in the some of these concepts. I might do instead of least recently used, least frequently used, I might change it to most frequently used. So if I did change it to most frequently used, what would it replace in this case? What page would be picked to be replaced? What has the most hits? 2. That's interesting. We'd pick 2 in both cases. Kind of cool. So what do you think of this? Does this explain that concept to you guys? Good. Good. All right. Okay, we have 10 minutes. I don't know if we have enough time to show the other example, but I'll put it up there, and I don't see it right now. I'll worry about it next time. I'll pull it up next time. I just don't see it right now. I had it. Oh, maybe I do have it. I have that. Maybe that is it. Yeah, this is it. This is the dynamic address translation problem. That's worth 5 points. And there's the 5 points. And the idea is you've got these tables in memory, and these are the virtual addresses, and then you're going to put a real address that's going to go in. And I'll talk about this next time. And I'll also review all these things with you on the review, the night of the review before the test. Okay, questions? Covered a lot of stuff tonight. Don't need that. Okay. You know about the team, so I don't need to worry about that. You know about the project. And I closed my note window. Any last minute questions? Okay, what's due? Let's look at what's due this Sunday, and then we'll close out. By the way, this completes half the class. This is week 6, so we're halfway through the class. 3 things, looks like. CC Confer question, which I answered earlier. The Chapter 8 questions and Chapter 9 questions. 4 questions. Okay, any other questions? Oh, this address translation question is what I just showed you. So you can take a look at it, right? Take a look at it, see if you can figure it out. I'll talk about it next time on Tuesday. But we're going to start Chapter 10 on Tuesday. Okay, guys, I want you to have a great weekend. Thank you for participating and being present. I really appreciate that. It makes it much more fun when there's a lot of people. Thank you. Usually this class seems to take more than 1 whole day to get on YouTube on Canvas, but I always try to get it by the end of Friday. But it might be until Saturday before it really gets placed on. Good night.